Okay, so I had a few slides left for Java which I won't cover today because, as I said, I'll switch over to algorithm analysis for the rest of this talk class, and then we'll do Java again next class. Okay, so this section of the class is about algorithm analysis. You may have seen parts of it, bits and pieces here and there, but we'll do it systematically. So the goal here is to reason about algorithms, and in fact even before we do that, we'll talk about how to describe algorithms. Then we will see how to analyze the efficiency of algorithms. Typically when we say efficiency, we talk about runtimes. The same methods can be used to analyze memory requirements and other sorts of metrics that people use, but the most common one, and certainly the one we'll focus on, is the runtime analysis. And the objective of all of this is to compare algorithms. The objective is not to say this algorithm we design or this data structure we are going to use in this algorithm is going to run on this particular machine, whatever they have here, in 3 microseconds. So we will not be able to do that. What we will be able to do is say, you have algorithm A and algorithm B as candidates for use. Which one is more suitable for me? Okay. Of course, that depends on how big my data is. We are going to focus on large data sizes because that's when algorithmic efficiency is the most crucial. The bigger the data, the more efficient your algorithm should be. So that's what our analysis is going to target. Right? So we want to be able to do a comparative analysis rather than say this is going to take 3 nanoseconds or 5 microseconds or something like that. That kind of analysis is much more difficult. It's hard to do it mathematically for reasons that we'll see. Okay, so before I talk about algorithms, let's talk about pseudocode. I've talked to people that have taken this course before, and one of them particularly complained to me saying, you know, the whole term we worked in Java, and then in the test we were asked to write pseudocode, and it was so difficult. So it really should be the other way around. I mean, think of pseudocode as writing Java-like code without having to follow the exact syntax of Java. But anyway, what I took away from that comment was that people weren't used to using pseudocode, and so let me talk about this a little bit, what pseudocode means, why would we use it, etc. So the idea is to use more or less English-like language than Java, because if you write Java code and you miss some semicolons, or you write equal instead of equal, or make some small syntax errors like that, you know, the meaning changes, and at that point I could penalize you for having written a program that wouldn't compile. But typically in tests we are not looking for syntax, we are looking for ideas or solutions to problems. Similarly, when I'm describing an algorithm to you, I certainly could open up Eclipse and write Java code here, and that would be fine. I would make mistakes and I would go back and fix them, and it would, you know, we could all do it that way. Or I could say things in at a much higher level of abstraction. So I would say things like, you have an array, use merge sort on this array, and then that sorts it, let's say, in increasing order. Then I use binary search to do the following, etc. So in the sense of communicating an algorithm, personally I find that English description easier than just punching out code for merge sort and punching out code for binary search and all of that. Right? A, it takes longer. B, I would probably make a lot of mistakes. And C, you do want to see sometimes things at higher levels of abstraction. Okay? When I buy a TV, I don't open up the back and see the boards and try to figure out what circuits they're using. I just want to watch TV, right? So, so there are places where you want to go into the guts and see what they are doing. And there are other times when you just want the higher level of abstraction. So pseudocode is really that. In pseudocode, you can write one sentence to describe something whose maybe shortest implementation in Java would take you 50 lines of code. Okay. Usually we follow some conventions, otherwise you and I are not on the same page when we are describing things. But by nature, pseudocode is not supposed to have a whole lot of rules. Otherwise, we might as well just write Java, right? So we assume we are allowed these simple constructs that every programming language has, right? So if-thens, whiles, repeats, fors, etc. Depending on the convention, we can use indentation, we can use braces. Indentation is more sort of the Python flavor of things. Braces are more C, Java, etc. Very often people do hybrids. Like you'll see when I have code on my slides, I use a formatting package that uses indentation. And I don't know if you've programmed in Python, it's a royal pain, unless you're using a Python IDE, it's a royal pain to put in all the indentations. But once you put them in, it does make the code fairly easy to read, right? Anyhow, so we are allowed to define methods just the same as any other programming language, as well as Java. We are allowed to pass inputs to methods, like here, maybe it has one compulsory argument and then an optional list of arguments. You can specify the input, you can specify the output, all very simple. You can specify a return value when there is a method, and we'll see examples in a second. So just like in many languages you use equals for assignment and equals for equality testing. On my slides I'll be using this left arrow for assignment and equals for equality testing. Okay. You can use superscripts and other such mathematical formatting because we are doing it on the screen or on a piece of paper rather than in an actual programming environment. Okay. So I should mention that if I ask you to describe an algorithm, let's say in a test or in an exam, you can write in English. So take array A, call quicksort on it, then on the first half of the array do this. You can say that, no problem at all. You can write pseudocode. You can write very close to or actual Java if you like. Personally, I prefer to not read Java, but I'm certainly not going to penalize you. The problem with reading Java is that you should document it properly. Otherwise, it's very frustrating to read 10 lines of code, even something small as 10 lines, without any documentation. Okay, and I'll show you examples in the next class. So I'll give you some 5-6 lines of code and ask you, what does this code do? Okay. But feel free to use any one of those three. The advantage of using Java or any actual programming language is it's completely precise. Okay, there's no ambiguity in any Java instruction. Okay, it's not that you can interpret it this way or that way. There's an absolutely precise meaning with no room for any ambiguity. Pseudocode is somewhere in the middle. English is or any human language, actually, any natural human language, but certainly English as well, is very vague. Okay, we don't communicate like computers. All our communications have shades of meaning, and if you are trying to do mathematical reasoning with shades of meaning, often things get very difficult. Right? So even the word is. What does is mean? So you're probably too young, but when they to remember all of this. But when they tried to impeach Bill Clinton, his defense was, is has a certain shade of meaning, and so he was able to sort of avoid conviction because using the semantics of is. Okay? And at some level, it's not completely false. When we say the sky is blue, we know that the sky is not blue, right? But it's something we say. Well, so the statement, the sky is blue, and this board is green. The semantics of is not the same for both, right? This board indeed has, below the glass, has a green layer of paint. The sky just looks blue because of, you've read it in physics. Why? Okay, there's no blue layer in the sky. Anyhow, so the point is, if you say things in English, please be aware that you should put in as much effort as you can to make it precise and unambiguous. Okay? If your answer, if your algorithm description is ambiguous, I'm trying to grade you. Of course, I cannot run that code because it's not code, but I also cannot determine whether you meant the correct interpretation of that answer or the incorrect interpretation. And I have to make a judgment call on, which is it. So those are the pros and cons. Anyhow, we will see examples of pseudocode as well as examples of Java code in the slides today. So when we are reasoning about algorithms, the first thing to specify is what is the input and what is the output. Okay? We will see that, in fact, in the second bullet, you see that correctness is defined in terms of valid inputs. So our definition of correctness, and notice that this says nothing about robustness. That's a software engineering concern. Here we are trying to be very mathematical. So we say our program is correct as long as it satisfies the output specifications for every valid input. Okay? What it does on the invalid inputs, we don't care. Okay, in real life, we care. For our mathematical characterization of this as correct or incorrect, we don't care. Okay? And the reason we don't care is our definition is very simple. We are given some output specification, which is a mathematical statement. If for every valid input that specification is achieved, then the program is deemed correct, or the algorithm is deemed correct. For invalid inputs, there is no notion of correct answers, right? So what does it have to be? You have to put in some extra specifications. So if it's, if you already have specifications for something that's invalid, then is it really invalid? You've accounted for that, etc. So let's keep things simple. We'll say we have a precise description of the inputs. In this case, let's say our example is sorting, something we have all seen. So the input is A1 through N, an array of integers. By the way, so this convention, whether the array starts from 0 or 1, often leads to problems in pseudocode. Because you say that you're going to do something to elements 1 through N minus 1. That, whatever you do, the correctness of the result depends on whether there's an element 0 or not. If, for example, there's an element 0, you haven't looked at it, well, your algorithm is incorrect. So again, be precise about these things. Either use the Java convention where things start from 0, or use the pseudocode convention where things start from, in my pseudocode convention, I should say, things start from 1. Okay? And so 1 to N means N is included. So again, also in for loops, right? In Java, if you say, or C, you say 0 to N, it includes 0 but not the N. Right? In my pseudocode, 1 to N means 1 and N are both included. Okay. All right. So the input specifications, it's an array of integers, and there are N elements in the array. Very simple. The output says, and notice now we have to be very careful. Even for something as simple as sorting, the output specifications say a permutation B of A such that the elements of B are in increasing order, okay, or non-decreasing order, more correctly. Why do I have to say permutations? Because if I just said the output is an array A where all the elements are satisfy that chain of inequalities. if that's your definition of correctness, then your algorithm could replace or rewrite A and fill it all with zeros, and that should be a correct sorting algorithm because it satisfies your output specifications, right? So which is, of course, not reasonable. So we often, I mean, of course, you and I and everybody else knows that when we say sorting, we implicitly assume that the array is not changed. It's rearranged, but it's not, I mean, things are not deleted, things are not replaced, things are not inserted. It's the same original array, just rearranged. But you have to say it in the specifications, because otherwise, some algorithm that's not correct will be admissible as correct. Okay? You will see this skill being used, again, in that third-year course, where you write down specifications using something close to logic. Okay? And one of the reasons you do logic courses, part of 1019, 1090, is because of that use in software engineering. I mean, there are other courses that use logic, AI courses, for example, but that third-year software design course specifically will train you in the art of writing specifications. Okay? But I want to point out the issues here. Okay, so with that input and output specifications, the correctness is defined in that simple, intuitive way. For every valid input, the output specifications must be satisfied by the output of the algorithm. Okay? We are not going to actually do correctness proofs today, so that's a topic for a later lecture. Today we are going to look at the analysis or the computation of the runtime of the algorithm. You know that we could talk about runtime or other metrics. As I mentioned, we'll talk only about the runtime here. Okay? In fact, what we would like to do is to express the running time as a function of the input size. So right there you see we are not going for a number. We are not asking for this input, does it take 3 microseconds or 4 nanoseconds or whatever. We're not doing that at all. We are saying if the number of inputs is n, what function expresses the running time of your algorithm? Okay, is it n squared? Is it n log n? Is it 2 to the n? Is it, what is it? Okay. One thing to be careful about is what constitutes input size depends a little on the application. Right? So if it's something like sorting, where you have, let's say n numbers stored in an array. Well, each number, it's a number in Java or any other programming language has a fixed size. It depends not just on the programming language, but also on the operating system and so on. But it's something. It's between 0 and whatever you can hold in 32 bits or 64 bits or whatever. But it's in a fixed range. Some applications are not like that. So for example, there's an example there, finding the factors of a number n. Okay, so there's one number there. It just happens to have lots and lots of bits. 100 bits, 1,000 bits, 2,000 bits. Okay. Why is this important? This is crucial in cryptography, and in particular, the encryption-decryption scheme that you use for almost all e-commerce, and not just e-commerce. When you do any kind of secure browsing, HTTPS, when you do SSH, you're logging in from home into opening a terminal in a machine in our computer science lab. Any of those things use something called SSL, Secure Sockets Layer. And SSL is based on a crypto system called the RSA crypto system. And the RSA crypto system is based on this problem being hard. Okay? If you are able to factorize large numbers fast, e-commerce, as you know, is out the window. Okay, so you should stop. Somebody say what? Every crypto system is based on some assumption, right? So some problem being hard. Because if the problem weren't hard, then you could break the crypto system, right? So every crypto system depends on you and I being not able to do a particular thing in a short amount of time. And for RSA, this is this, not being able to factor large numbers. And as I said, What constitutes large depends on what version of RSA they're using. In the old days, they would use smaller numbers because with the computers available in those days, those numbers would be infeasible. Today, you could break those. So they've increased the number of bits in these numbers. Okay? But again, I mean, coming back to our point, it's one number. So do you say the size of my input is 1? No, because yes, it is one number, but the size is variable. You might be thinking of factoring a number with 50 digits. I might be thinking of 200 digits. Somebody else might be thinking of 500 digits, etc. Okay? So the input size in that case is not the number of numbers. There's only one number, but the number of bits. Okay? So you have to be careful about that. For the most part, these kind of subtle issues will not affect us, but it's something to keep in mind. Next, I mean, as you'll see, even something as simple as comparison of algorithms, there's so many complicating factors. Machine model. What is the architecture of the machine? Does the processor make a difference? I mean, in general, of course, yes, right? So it's not that a program runs in exactly the same time on a Mac and on a Windows machine and on a Linux machine. So what is it that makes analysis complex on real machines? The biggest problem is the memory hierarchy. Okay? What that means is if you take a typical computer, there is some on-chip storage. The processor chip has some storage on it. Okay? In particular, it's called the cache. So there's some on-chip cache. There's some off-chip cache. Off-chip cache is not as fast as on-chip cache, but it's close. Then there is the RAM, which are the memory chips that are on your motherboard. Okay? They are much slower. I mean, the chips are the technology is slower I mean, the memory itself is inherently slower, but B, the connection between the memory and the processor uses a bus that's slow. So accessing a piece of memory does not have uniform cost. In your program, you say x is equal to y. That means you take the value of a variable y and copy it into x, or assign x with that value, right? You are not thinking about where is y and where is x. Is it in the on-chip cache, off-chip cache? Is it in the RAM? Is it stored on disk maybe? Is it across a network? You know, some cloud storage somewhere. You're not thinking, I mean, as a programmer, you and I are not thinking of those things. But in reality, those things make a difference, right? Not only does it make a difference, it's even worse than that. It makes a difference in different runs of the program, right? So you take the same program, give it the same inputs. The only difference may be the first time that variable was stored in the on-chip cache, and the second time it happened to be not stored in the on-chip cache, so it had to be fetched from RAM. So that means running the same program twice on the same inputs, you get two different running times, which absolutely should not happen in our simplistic view of programming, right? The only time we would expect things to take different running times is if we use some randomization. You know, you flip a random bit, you do something if the coin toss makes it 1 or 0, if the random number is less than this, you do something more. In that case, we expect that yes, each time you flip a random bit or you generate a random bit, it takes different amounts of time, no problem. But in a deterministic piece of code, you expect reproducibility, right? You expect that if I run this code 10 times, I should get the exact same running times. And of course, that's not the case, right? In most modern machines, in fact, you are sharing the CPU. You're not the sole user of the CPU. Okay? You may be, even if you're the sole human user, you're sharing it with background processes that the operating system is running and so on and so forth. So that causes more variations. Okay? But it's mostly the memory hierarchy that's a problem. Okay? And so we avoid all that in our analysis. This is when we are doing something very simple. When you do architecture courses, you'll see other sources of variation. Modern CPUs are pipelined. Okay? So this idea of pipelining is based on being able to predict what kinds of computations will happen, what kind of memory accesses will happen, and prefetching data to make that faster. Okay, so if things go well, as soon as, again, in your program, you're saying x equals y. If y is not in the cache, but the operating system has a good predictor and things are working well, then that y will be brought into cache by the time that instruction operates, and you'll get faster access time to that variable. But sometimes prediction algorithms fail, so the cache has to, the pipeline has to be flushed. So everything that was brought in, you discard and you start the process all over, and so you take a hit in the running time. Okay, caching is used, by the way, on the web a lot. So if you've seen the word web caching, very, very common. Okay? For example, let's say York has, I don't know, 20,000. No, that's too high. 2,000 computers. I mean, I guess with mobile devices it's a lot more, but let's say computers. Okay, so York has 20,000 computers. Now, if there is a website that people visit, I don't know, cbc.ca, whatever, right? So even if like half those people are frequenting that site, cbc.ca, CBC web page, when somebody clicks or types cbc.ca, one option is to actually query the CBC server, get the page, and serve it. Okay? If that's all that's done, then you are putting extra load on that server by sending all these large number of users, but also presumably the CBC server is not on the York campus, so it's somewhere away, wherever it is, and each user is being served slower because that network access is going across some geographical distance. What web caching algorithms do instead is it keeps a more or less current version of the cbc.ca page in its local cache. And so as soon as you type cbc.ca, it serves you from somewhere local, not from the actual server. And so it minimizes traffic going outside York, and it gives you faster access times, faster response times. Okay. So that's an example of caching in that context. Similar things are done in the processor to reduce the time for memory access, for instruction access, data access, all those things. And if that works, you get one kind of running time. Occasionally, as I said, the prediction algorithms fail, so it has to be refetched, and so you get higher running times. Okay? So already the problem seems quite complex. What do I assume, and what is reasonable to assume? Okay? So the simplified machine model is unfortunately called RAM. RAM, not in random access memory. The chips that the memory in your computers or even mobile devices, when they talk about memory, they call it RAM, but that's random access memory. This is random access machine. Okay, it's a machine model. It's an abstract mathematical model of a real complex computer. And really, it's very, very simple. Right? It sort of throws away all the complexity. It says all instructions take constant time. Okay? Instructions could be, arithmetic operations, data movement, branching, method calls, whatever, comparisons. All of them take constant time. In reality, on a real machine, they do take constant time. As in, it's never the case that you can take arbitrary amounts of time for adding two numbers. But adding and multiplying and subtracting might take different amounts of time. In particular, multiplication takes more time than addition. Okay? And how much more depends on the processor architecture. It supports all the standard data types, so you don't have to worry. Most importantly, there is no memory, there is no network. The reason it's called random access is every memory access, memory as in variable, array, whatever, any data item that you access takes an equal amount of time. As I said, that's not true in real machines. And in fact, it's becoming even less true as time goes on. Anybody have any exposure to GPU programming, graphics units or graphics processors? No? Okay. Modern GPUs, so let's say for a couple of $100, you can buy graphics cards that have hundreds of, let's call them processors. They're not exactly full-fledged processors, but they're close. They call them cores, okay, using the same language as your 8-core CPU or your quad-core CPU. So graphics processors can have hundreds to thousands of cores. So think of, again, as I said, cores in the graphics context as processors with restrictions. They're not full-fledged, Core i7s. So if you ever have to write a program for those, you have to do your own memory management. You as a programmer, not OS designer, as a programmer. You have to decide whether a certain variable is stored in local memory or shared memory. Okay? And the complexity of doing that is enormous. The advantage, of course, is that if you can do it well, you get a lot of parallelism. Lots of things that are slow on your most modern 8-core processor, you throw 1,000 low-level processors at it, you get 200 times speed up or 75 times speed up. 175 times speed up is not a joke. You go from a minute to a second, less than a second, right? So very, very common, particularly if you are looking at learning algorithms. Very deep learning is the flavor of the day. Very, very computation intensive. There are good libraries for learning, good implementations of learning algorithms that make use of those high number of cores and run much faster than they would on the fastest 16-core machine of the day. Okay? Anyway, so all of those things are ignored. Okay? Okay, so this is our machine model. So really we are ignoring all the complexity or almost all the complexity of modern processors. And we're trying to say something about the comparison of algorithms A versus B, which one is going to run faster or slower. Okay? And we are going to focus on large inputs. Okay? So here's this first example of pseudocode, and you can see it's there's some indentation and so on. This is one of the simplest algorithms you can think about that uses a for loop. It finds the max of n numbers. Very, very simple, right? So line 2 makes the first element the max. Lines 3 through 5 sweep through the rest of the array from 2 to n, comparing each element with the max, and if it happens to be bigger, then max gets updated to that element. Okay? And finally, you return whatever is in max. Very simple, right? Nothing of any difficulty in the program or algorithm. So this is pseudocode, right? So there's no Java syntax, there's no semicolons, there's no braces. Hopefully it's pretty easy to read, right? There's nothing really, as I said, people have complained that this is very hard to write. Now, I don't see that, but if you find that, practice. You're just really reducing the syntactic requirements of Java and writing in a much more simple way. One can certainly look at the Java code. This is from the book, so the same exact thing, but with certain differences. So Java, starts the max at 0 instead of 1 because the array starts at 0 and not 1. It doesn't go up to n; it goes up to n minus 1, etc. But the same exact algorithm. Right? And so you can certainly compare, this one with this one. If the Java thing looks simpler, then by all means go for it. So we want to analyze the running time. Okay, and maybe you've seen, for things this simple, you may have seen this. If not, it's okay too. So what we are going to do is there are 6 lines of code. So we are going to, for each line, write down the cost and write down the number of times that line is executed. Okay? Cost in this case means time. Okay, you can think of any notion of cost, but so time can be nanoseconds, time can be processor cycles, what have you, but some arbitrary measure cost. Okay, so lines 1 and 2 are executed once, right? It's not part of a loop. Similarly, line 6 is executed once, just one it returns. 3, 4, and 5 are in parts of a loop, or they form a loop, right? For line 3, see the number of times is written as n, not n minus 1. Anybody guess why? Line 3, I claim, line 3 runs n times, but line 4 runs n minus 1 times. Why the difference? That's still the n, right? If the length is n, 0 through n minus 1 is n. Hang on, somebody else said. Yeah, 2 through n is n minus 1 though, right? 1 through n is n elements, 2 through n is n minus 1. Not, sorry, let me answer it. Not the assignment, because the assignment has a cost. I'm not talking of the cost here, I'm talking about the number of times that line is executed. Yes. Yeah. So, I mean, again, this is partly my convention. Real systems may or may not do it this way, but really the way for loops are implemented at a lower level is you keep incrementing j and checking against the upper limit. So the very last time j is incremented, it becomes n plus 1. So you say, well, n plus 1 is not less than equal to n, so the body of the loop is not going to execute. That's when I quit the loop. Okay? Again, it's a convention. You may or may not do it this way. It doesn't change anything essential, but in my case, this is how I interpret that. Right? So the first line of the loop is going to run once more than the body of the loop. So line 4 is in the body of the loop. So body means the code inside the loop, right? So line 4 is executed n minus 1 times, as it should. 2 through n is n minus 1. So that's fine. Line 3 is executed n times. What about line 5? Line 5, the problem is it's dependent on an if. And I don't, without knowing the actual input, I can't tell you how many times it's executed. Right? Yes. So I can talk about the best case and the worst case. I can say in the best case as in the case that will result in the fastest running time, it's never taken. Right? So intuitively it corresponds to max being the first, I mean the first element being the max. Okay? If the first element is the max and strictly bigger than any, actually it doesn't even have to be strictly bigger, but if the first element is the max, then the if test on line 4 always fails and line 5 is never executed. On the other hand, in the worst case, line 5 is always executed. So what constitutes, I mean, think of an input that will force line 5 to be always executed. Little bit more, yes. If it is sorted in increasing order, the second one is going to be bigger than the first, the third one is going to be bigger than the second, and so it's going to get assigned every single time, right? Okay, so now what is the total runtime? So I'm going to take the product of the last two columns and just sum it up. Right? The first line has cost C1 times 1. The second line has cost C2. It's executed once, so C2. The third line is executed n times. The cost is C3. So the final cost is going to be, or the time is going to be, if you like, C1 plus C2 plus C3 times n plus C4 times n minus 1 plus k times C5 plus C6. Okay? And I cannot say anything, as I said, about k, but I can certainly plug in the two endpoints for the worst and best cases, and that way I get different runtimes, different times for the best and worst case. Okay? In general, the input may not, I mean, not all inputs correspond to either the best or worst cases. You get something in between. The case that line is sometimes executed and sometimes not executed, right? So if you want to plot runtime, so let's say I have the x-axis is the size of the input. So let's say I've done it for arrays of size 1000, 2000, 3000, and 4000, and my running time on the y-axis I haven't specified units, so whatever units they are. There are 3 bars for each size. One is the best case, one is the worst case, and one is the average case. An average case simply is however many runs I have done for each input size, I add those up, I divide by the number of runs, and that's my average case. Okay, so you really get 3 different numbers. If I'm doing it experimentally, which is the assumption here, I run it with different inputs and I take the average of the runtimes. There are more complicated notions of average case which we'll come back to, but so which one should you take? Best case is usually not very helpful, right? So yeah, your algorithm in the best case runs very fast. What does that really tell you? Not a whole lot, right? The average case is good because I use my sorting algorithm 1,000 times a day, or my code uses it 1,000 times a day. On average, I see this amount of time or this function. That's good to know. The problem is it's hard to compute. Okay. Experimentally, I said if I'm evaluating something, I just add all the runtimes and I divide. That's fine. But in the long run, what inputs do I use to generate that average? Okay. In other words, are there some inputs that are more likely and some inputs that are less likely? Or is it that my inputs are always going to be random? So depending on the answer to that question, I'm going to get different estimates for the runtime, for the average case runtime. Right? In reality, often there are some inputs that are, or some set of inputs, subset of inputs that are more likely and some that are less likely. It's not always uniform, but that non-uniformity is very hard to capture. Your typical might make some subset more likely. His or her typical may be different. So it's useful but hard to determine. So at least in introductory courses like this one, we focus on worst case. Okay, worst case is easier to analyze, especially mathematically. Experimentally, not so much. Because especially if you don't know a priori what kind of input will create the worst case runtimes, then the standard way is to generate random inputs. And depending on how frequent the worst case is, you may have to generate lots and lots and lots of random inputs before you see anything that's close to the worst case. Okay? But for doing mathematical analysis like what we will do, it's relatively straightforward. Okay? And it's useful in many different applications, and this lists some. But okay, so how do you do experimental analysis? There's a time command in Java. You can read it from there, system.current.time in milliseconds. So you insert that, then you put in the chunk of code that you want to run. So you measure the start time and the end time, and the difference is the runtime of your code. Okay? And you do that a whole bunch of times. Okay? Why more than once? Well, because you're doing it with different inputs, but we have other sources of variation, as I mentioned, even with the same input. So in this case, he's shown you only 3 runs for each. Hopefully, if you're trying to do something and get reliable answers, you have to do it much more than 3 times, but some number of times. For each, the x-axis typically is the input size, the y-axis is time, and so for each input size, you generate different inputs of the same size, in this case 3 different ones. You measure the runtimes, and if you're lucky, they map very cleanly to a curve like this. So you fit a curve, and that gives you at least an approximate expression for the running time of your algorithm. Now, if you have to do it, if you have to measure runtime reliably, the first thing you need is an efficient implementation, because you may have a great algorithm that's implemented very badly. Your inference from the measured runtimes is not going to be very accurate. Okay. So what we are going to do is to do it with paper and pencil. Okay. And you'll see how in a second. You have to do some math review, unfortunately, so let's do that. The book actually makes it somewhat easy and talks about these 7 functions. Okay, these are very common functions, but these are the most common functions that you encounter when you're measuring running times of algorithms. Okay. Notice that I have approximate signs for each. We'll define what this approximation is, but roughly speaking, we talk about constant runtimes. Constant means a number, 2, 3, 4. Constant relative to the input size. So an algorithm runs in constant time if the running time does not change appreciably if you increase the size of the inputs more and more and more. Okay. Then you have a logarithmic time. If you've seen binary search, you know at least one algorithm that takes logarithmic time. Linear time, anything that sweeps across an array, calculates the sum of the numbers of an array, finds the maximum. All of those take linear time because you have to look at everything in the array. N log n time most commonly you see for sorting. Okay, the more efficient sorting algorithms, merge sort, heap sort, so on. Quadratic time you see in the less efficient sorts. So quick sort, insertion sort, selection sort, all these have worst case n squared running times. You see, I don't know if you've seen any algorithms with cubic runtimes. There's one on, I think, the last slide in this set. It's for matrix multiplication. Doing matrix multiplication with no smartness added in, the naive way, is one example of a cubic time algorithm. Okay, there are many other examples. And finally, something that's exponential time. There are many problems that we do not know faster algorithms for. So anytime you have to do brute force exhaustive search, chances are that those are exponential time algorithms. There is some, this is a graph from the book. It just shows you the relative growth rates of these different functions. The one thing I'll point out is that the axes are not linear, they are logarithmic. So in the distance between 10 and 100 and the distance between 100 and 1000 is the same. Okay, so that's the nature of logarithmic axis. This is called a log-log axis or log-log graph. In certain applications you need only one of them to be log, the other is linear. Depends on what you want to see. Okay, and the reason is, so for example, the difference between a quadratic function here and a linear function there, both of them are straight lines. Right? So linear function you'd expect to be straight. Why is the quadratic function a straight line? Because once you take logs, log n is log n squared equals 2 log n, right? And the axis is logarithmic. So in logarithmic axis, this has twice, it's a straight line first of all, and it's twice the slope as this. Whereas on the normal linear axis that you're used to, this would be a linear function and this would be a quadratic function. It wouldn't be a straight line. Okay? Just something to keep in mind. It's not that you cannot draw or you should not draw them with linear axes. The only problem would be that many of these curves would just shoot out of the range of your, so just like you have one of them going vertically up, many of these other ones would also kind of go that way. Okay? Here you can see a lot more of the curves on the same graph. I'm teaching, I teach the engineering section of discrete math pretty much every year. I find people to have lots of problems with exponents and logs. Okay? So if you're fuzzy on those, please review the slides. I'm not going to talk about each of them, but there's very standard facts on logs. One that always gives people trouble is this 2 to the power log base 2 of x is x. Okay? The easiest way to see them, well, there are two ways. One is you can take logs of both sides with the base a, and you'll see that both sides are equal. But a more intuitive way is to say exponentiation and logarithms are inverse functions. So if you take a to the power and log based a, they are inverse functions, so they cancel each other. So you get back b. Okay? But whichever way you want to look at it, this is simple stuff, but you should have them handy, otherwise you get stuck when you're reasoning about algorithms. Similarly, facts about logarithms, they're on the slides, it's also in the book, brush them up. Series sum, that's very useful. Again, you should have seen this before, but if not, here is a nice picture. 1 plus 2 plus up to n, that sum is n times n plus 1 over 2. Okay? It's certainly easy to prove this in many different ways, but notice that this is a pictorial proof. Notice that the green bars and the blue bars, they're exactly the same. So this is 1, this is 1, this is 2, this is 2, 3, 3, 4, 4, 5, 5, 6, 6, etc. So the blue and the green are equal. Together you have, if you have n here, you have n plus 1 here, so the total area is n times n plus 1. So half of that is n times n plus 1 over 2. Okay, it's a cute proof, but if you don't like the pictures, then what you can do is you can write the series forwards and backwards. So 1 plus 2 plus up to n, write the series backwards, add them up, kind of column by column if you will. So each of those columns is n plus 1, and there are n of those columns, so this is equal to n times n plus 1. So this is the original series, so this is 2s, so s is equal to half of that. There are any number of ways of proving this, it's not hard. And you don't even have to remember the proof, just remember the fact. Okay, so we'll get to using that, not in this program, but in a following program. So we have these best and worst case runtimes. We haven't talked about the C sub i's. Okay, what are they? Well, on a real machine, they are actual runtimes, 3 nanoseconds, 5 nanoseconds, whatever it is. Here, to be general, we have kept them as C sub 1 and C sub 2 and so on. So you might ask, line 1 is an assignment, line 2 is also an assignment. Why are they unequal? Why didn't I write C sub 1 for both? Okay. A, it really doesn't matter. We're going to throw away all the C's in a second. B, maybe getting the first element of an array is different from getting the length. The length maybe you get through a method. The first element maybe you get through another method, or whatever it is. Is the array something that's accessible? Is it inside some sort of a class where you need to go through a method, or is it just accessible as private memory that you can access the first element of, so on. Okay. The point though is that this is still kind of complex. I don't know what C3, C4, C5 are. There's some positive terms, some negative terms. How can I simplify it? Okay. So one simple idea is to say, okay, since I don't really know what these constants are, maybe I can aggregate them and call this part uppercase C, call this part uppercase D, and I get a function like this, which is simpler, but can we make it even simpler? Okay. We've seen before that we call linear functions n. Now from algebra or from other courses, calculus, you know that n is not the only linear function, it's a n plus b really. But what we want to say is this whole thing is something like n. Okay. So what do we need? What mathematical constructs do we need to be able to just say this is roughly equal to n and throw away the c and the d as well. Okay. So before we see that, why do we want to do that? Well, first of all, we are interested in large n. Right? So if you look at this function c plus dn, c is a fixed number. So the effect of c as a number on the numerical value of c of dn, c plus dn, will fast decrease as n is increasing. Okay, so for high n's, d times n will really be much bigger than the c. So you can kind of forget about the c. Okay. The d, the multiplicative constant, or what I call coefficients, that is machine dependent. And so I don't really know, for one machine C1 might be 3 nanoseconds, for another machine it may be 2 or 1.2 or whatever. So I really don't care about it, so I want to throw that away as well. Okay, okay, so I'll get clarity or ease of manipulation if I do that. What I will lose is I will get even less exact about runtimes. Already I was not predicting numerical values of runtimes, but now I've thrown away even more information. Also, throwing away C makes sense in the previous slide. Throwing away C makes sense when n is large. It may not make sense when n is small. So once I throw C away, my predictions or my claims for small n will get even more approximate, okay, even less reliable. And if the difference between two algorithms is, I mean, both are of the form c plus dn, but the c's and the d's are slightly different, 2 plus 3n versus 4 plus 2n. If I throw away those numbers and I reduce both of them to n, well, I lose that distinction completely, right? So all those things I'm going to lose. What am I going to gain? Something, if it was linear, it could only be of the form cn plus d. If it's quadratic, it could look something like that, 3n squared minus 5n plus 6. I am going to be reducing all of that to say n squared. What is the intuition? The intuition is n squared is the largest term. The leading term, the most dominant term is the square term. Okay? The n square part grows much faster than the n part. The n part grows much faster than the constant part. The constant part doesn't grow at all with n, right? So really, if you are thinking about large n, that n square term is the dominant term. Okay? So in some sense, that is the essential information. How does this scale? What is the largest term in the runtime as a function of n? Well, it's n squared or n cubed or n log n. Okay, that's what we are shooting for. Okay, so we still need some mathematics. Have people seen big O's before? That is roughly okay. So I'll define them mathematically again. F of n is, sorry. Notice that I use belongs. Why do I say belongs and not equals? It's a set, right? So many functions are O of n. So it doesn't make sense to say one function equals a set. But as I point out in one later slide, people write equals all the time, and when you see that, you have to map it mentally that they mean belongs, say equal. Okay, so Fn, we often say is, instead of belongs, we say is. Fn is OGN if Fn is less than equal to C times Gn for all n greater than some n sub 0, and C has to be a positive constant. Okay? So for example, 2n plus 10, I'm sure this you've seen before, 2n plus 10 is On, 3n squared minus 5n plus 6 is On squared, but it's also true that 2n plus 10 is On cubed. It's not the most meaningful statement, but nevertheless it's perfectly true mathematically, right? So one way to think about big O is the rate at which Fn grows is no larger than C times this Gn. So in this case it would say a linear function grows no faster than a cubic function. That's a very weak statement, right? Of course, the cubic function grows much, much faster. But we are just saying this is no faster than the cubic function. Okay. So here's a picture. Typically, you choose Gn to be simple. F of n is what you get from analyzing your program, your algorithm. Maybe complex, or at least certainly more complex. Gn, you choose something simple, n squared, n, one of those 7 functions, let's say, that we looked at. So because you chose a simple function, it may not be the case that the blue curve, the simple function, is always above the red curve. So what we ask is that there should be some threshold. In fact, you see the k is here. We could have shifted the k to this point at most, right? There's some threshold k, the graph, because I took it from one place on the web, it says k. For us, that k is n sub 0, right? So there's this threshold n sub 0 to the right of which the blue curve is always above the red curve. Okay? If that's the case, then we say f of n is big O of g of n. Simple. If you've seen big O, you've probably seen big omega, but even if you haven't, this just reverses the inequality. Instead of saying less than equal to c times g of n, we are saying greater than equal to g of n. Okay? So the way to read this is f of n grows at least as fast as cg of n. And more precisely, f of n is greater than equal to cg of n everywhere to the right of some threshold n sub 0. Okay. So again, examples: 2n plus 10 is big omega of n, 3n squared minus 5n plus 6 is big omega of n squared, but 3n squared minus 5n plus 6 is big omega of n as well. Again, not the most accurate statement you can make, somewhat weak, but it's perfectly correct. The left-hand side is a quadratic function. It grows at least as fast as a linear function, right? Which of course is true. Okay, what if you wanted to make really precise statements? Then you want to use this notation called theta. Very simply, theta f of n is theta gn if f is both big O and big omega of g of n. Okay. So we can combine the two inequalities like this. There exists some constant, positive constant c1, some positive constant c2, and some n0 also positive. Positive, by the way, does not include 0. Okay. Students make this mistake very frequently. 0 is not positive. 0 is neither positive nor negative. So when we say positive, we mean greater than 0, strictly greater. Okay, so f of n is between these two. Okay. Pictorially, this is how it should look like. There is some threshold here. Again, he calls it k, I call it n sub 0. To the right of n sub 0, the function g multiplied by a bigger constant is this upper blue curve, multiplied by a smaller constant is this lower blue curve, and the red line always stays between the two blue curves. Okay. Okay, so again, let's look at our examples. So 2n plus 10, of course, is theta of n. Both sides are linear. 3n squared, etc., is theta of n squared, quadratic on both sides. But the other two weaker statements we made, they are not big theta. Oops, I'm sorry, this should have been big theta. The omega is actually true. So I'll fix this. So 3n squared minus 5n plus 6 is not big theta of n. 2n plus 10 is not big theta of n squared. Okay. You might ask, why do we not always use big theta? Why do we have even big O's and big omegas? The short answer is, oftentimes when you design an algorithm, it's hard to compute the exact runtime. It's often easier to prove one of theta and omega, but not both. Okay. Now some abuses of notation. I mentioned the first one. You often say equals when really, strictly speaking, you should say in or belongs to. More annoying, especially in engineering, unfortunately, people often say big O and mean theta. Okay, and you have to be able to correct those mentally. Strictly speaking, as we saw, big O and big theta are not the same. Big O is weaker, theta is more tight, but people somehow, for some reason in electrical engineering particularly, people interchange those two and mean the same thing. Okay, some colloquial uses. Theta 1 we call constant. Okay, now a constant we understand, it's a number, 2, 3, 5.7, pi, right? Theta 1 allows not just constants, but things that are within constants. So, I mean, usually you'll never have a running time as sine of n, but let's just consider that as a function. Sine of anything is between -1 and +1. So it satisfies the definition of theta 1, even though it's not a constant. But colloquially, since those kind of weird functions don't exist, don't occur in runtime analysis, we associate the word constant to theta 1. More confusing, sometimes people say n to the theta 1 and call it a polynomial. Normally, at least until now, if somebody said polynomial, you would be thinking integer powers of x, n, let's say. Maybe sums of integer powers, n plus n squared, or n to the 3 plus n minus 3, something like that. Normally you wouldn't call n to the power 0.001 a polynomial, right? But again, in computer science, people have sort of abused notation a little bit, and we will call n to the power any constant we will call a polynomial. 2 to the power anything times n, or an plus b, we will call exponential, even though, again, strictly speaking, an exponential is 2 to the power n, or 2 to the power 3n at most. I mean, some constant times n, not some constant times n plus some other constant. A couple of mistakes to avoid. N to the theta 1 is not theta of n. Very simple, right? Because n to the theta 1 includes n squared, n cubed, n to the power 100, n to the power 5 million. All those are n to the power theta 1, and certainly they are not theta of n to the 1. Okay. Less obvious perhaps, 2 to the power theta n is not theta of 2 to the power n. So in fact, 2 to the power 2n, let's say, it's actually 4 to the n, is not theta of this one gets people, but I mean, you can plot those graphs, for example, and you can see, right? 2 to the n and 4 to the n diverge. In fact, one is the square of the other. So you don't expect n and n squared to be within constant factors of each other, right? To be theta of each other, they have to be within constant factors. Okay, I'll stop here after this slide. Very simple things you should remember, even after you've forgotten the formulas. Logarithmic functions always grow slower, much slower, but slower than polynomials. Linear functions much slower than quadratic, and polynomials are slower than exponentials. So just an examples, you can take log n, raise it to a huge power, and compare that with n to the power very small number. This is still smaller. Not for small n. For small n, log to the 1000 n will be much, much bigger than n to the 0.0001. But eventually, okay, so for sufficiently large n. Similarly, you can take a linear term and multiply it with a relatively large constant. You can take a quadratic term, multiply it with a relatively small constant. Still, the linear is going to be less than quadratic. And similarly with polynomial and exponential. I'll stop here.